This is the second part of the Improve video series. It focuses on the measure phase. Having discussed earlier an overview of the methodology, and the define phase, the scoping phase, was illustrated in particular with respect to an example of competitive bidding, developing a bid proposal in response to RFQ. The next one will be on analyze. In this video, I will look at a number of key concepts: variables, variation, measurement, measurement systems, process capability, statistics, statistical distribution, voice of process, voice of customer, capability improvement, process shift and drift, granularity, the techniques, capability calculations, and process mapping. On the first part, I will discuss variables in the context of operational processes. What exactly is a variable? What are we talking about here? Let's take a simple example of a checkout process at a grocery store. There are many variations of the way this is done, but basically you've got a customer coming in with a basket full of groceries, and you've got a clerk at the other end, and the customer empties the basket, and the operator scans barcode, types in a number of stuff, weighs at times some stuff that has to be weighed. And we could do a process mapping of this, with the rows being the customer, the clerk, cashier, the wrapper, the various technologies. There's the computer, there are systems and databases, there's the payment system, there's a scale, there's a barcode, and all these are actors as well. So the actors are human and technologies, and way in the back office, systems and databases as well. They're all players in the same transaction. Input, output. Input, a customer with a basket of goodies. Output, a customer processed, thanked, having all his stuff, having paid for all his stuff, and leaving happy, hopefully, with a firm intent to come back and say, what a nice place. I really love shopping here. The transformation in between, of course, is detailed in what I just described. We could map it, and as we map it, we could see what the variables are. Like, in terms of big Y, speed of transit. How many transactions do you process per hour? What percentage of accuracy do you get in the amount you collect versus the actual amount, the actual things that have been bought? Did you collect everything? Did you overcharge? Did you undercharge? That is certainly quite critical as well. In terms of operational variables, the time of each operation. How long does it take for the person to take one item, and how long does it take to empty a basket? That will vary on the size of the basket, of course, so there will be variations. How long does it take the operator to scan? How long does it take to process the whole order? How many items are left below the basket unseen and uncharged, intentionally or not? Those are variables in a process. This is an alternate process where the customer self-checkout. It's a different process to achieve the same means in the end. Let's move to another area, a bank. Input, customer in, wanting to do some sort of transactions. Output, a satisfied customer, transaction all realized, and again with the feeling of saying, what a great place, I love coming here once in a while. Let's take a specific market segment and a specific transaction this time. Students. Let's say it's September, we are near a campus or on a campus, and new students are opening account. New undergrad and new graduate students are opening account. This is a specific transaction, and I just look at the mapping on the web here. It's about a student account opening process in a branch, where you've got the line of visibility, meaning everything behind here the customer doesn't see. Many operational aspects are invisible to the customer, but not inconsequential. They are closely connected to actions within the field of visibility. Customer comes in, some graduate students, some undergrads. Do they go straight to get the application form? Or do they go to the counter to get some more information? Do they decide to go for it, or do they decide to come back? Do they go to fill right away? You've got all the flows here. And we could, of course there are many variables, but sometimes the mapping we've done is just too high level, too coarse, to allow for clear visibility of the variables. For example, so you zoom in, interact with clerk, discussion, choice between undergrad, grad program, the various types of options that they have available. What are the variables in here? Just for sake of illustration. Frequency of balking, reneging, and jockeying. For example, balking is I see a line of 10 people, I just walk out, come back next time, or go to the other bank in front. Reneging is I stand in, look at the pace of it and say, no way, I renege. Or I see 5 lines and I jockey from one to the other to try and get faster there. So that's those are variables. You can measure the frequency of that. Waiting time, average, medium, maximum span, duration of the activity, percentage of graduate and undergraduate student to decide to go for the application, those who walk out, socioeconomic characteristics of students according to the decision. Those are variables. Are they relevant? Depending on our purpose, what are we trying to improve here? The hit rate, the proportion that go for it, the time they take doing it, the amount of money they will put into it. Depending on our big Y and small y, what goal are we trying to achieve? Some variables may be relevant. At this point, we have to merely identify those variables and then find a way to measure them. If you can't measure it, certainly you won't be able to work on that variable. Some variables you control, some you don't control at all, some you control partially. Other example, pharmacy, input customer with a prescription, output customer going with his stuff, happy to be there. Zoom in. This is the flow of the process with the players, the customer, the contact person, which may be a tech, the pharmacist at various points in time, various pharmacists, and way back there, there's the doctor that may be called in to verify something about the prescription or the particular patient's file. You've got the flow with times, minimum time, maximum time, and then prescription. Contact person takes prescription, locate the customer. Are you really Mr. So-and-so, blah, blah, blah. Interactions. You've got the flow here going there with verification, with various players involved and various technologies involved at various points in time. It's important to get the granularity right, to get it at the same level of granularity, and to get it at a point close enough, Google Street View style, where you can see the important variable. At this point, you're not trying to discriminate. You're trying to logically think, hey, this may be important. Can I measure it? Identify the variables. Then we will get the data. Then we will analyze it. Next phase. Zoom in. Pays and leave. And processes the payment, of course. If you just zoom in on that part, customer pays and the payment is processed, and you do a detailed street view level mapping of that, the players are the customer again, the contact person, the computer terminal, the handheld payment terminal, the barcode scanner, the printer, the authorization system. How are you going to pay, sir? It'll be debit for me. Okay, here's the terminal. Scan. Oh, I scan, of course, the invoice before. Scan the invoice, the computer retrieves the record. Information is sent to computer. He gets the terminal, puts his card in. The information is sent back to a back room, way somewhere, algorithm that will look at the credit of that person, may access a database, may use system to detect that something is wrong, and may actually involve a human being if something is very wrong, and then we'll send a decision which will say, okay, payment, you can withdraw your card and go back and so on. So that's a zoom in at which level variables are visible. When you do mapping, make sure you maintain the same level of granularity. It's good practice to start with a high level view, macro map, and slowly take it down. And as you go, select and zoom into the more important part. Skimming over at 5,000 meters is nice, but you will not see the problems or the opportunities down there. So if you zoom in, just the algorithm here, receiving customer information and deciding whether $500 is a good credit decision, requires systems, access to customer data, access to credit bureau information maybe, and logic and intelligence to detect that something may be wrong. This customer has never been in France before, and he's buying medication that we've never seen before. Something's wrong. Red light intervention. Many variables involved in here, and consequence as well. Moving on. This is referring back to the example of the IT company bidding for system development contracts that we discussed earlier. This is the type of process that will go on, and you can map this as we have in the past, and you get in an RFQ. Finance reads, assess, and recommend. Everybody, the technical side, the planning side, they prepare a commercial solution, a technical solution, risk analysis, and so on. There's time involved, there's cost. You can again zoom in to get the required detailed granularity. For example, risk assessment. What is risk exactly? What types of risks are there? How do we measure it? Can we measure it consistently? And can we decide on thresholds and adapt our decision to bid or no bid, or the markup we're going to apply to this situation, or conditions we're going to put in, terms and conditions in our bid? That's measurement system. And so we need to go through a number of definitions here about measurement, variable, risk, uncertainty. Those definitions, many of which come from How to Measure Anything, Douglas Hubbard. It's a very good book, by the way. Uncertainty. Uncertainty is the lack of complete certainty. That is the existence of more than one possibility. The true outcome, state, result, value is unknown. Risk involved that depending on the state of nature, you've got consequence, which could be catastrophic, undesirable outcome, financial outcome, which is the case in the software development case, of course. Measurement is a set of probabilities that are assigned to a set of possibilities. In this software, what are the possibilities that we are unable to make a bridge between this and that system, or that the interface between this database and this access system will be problematic and will require 2 more weeks of work, or the purchase or the use of an additional subcontractor for that? Question mark. Measurement of risk is assessing probabilities and seeing what are the costs associated with it. Just uncertainty is one thing. Risk involved that depending on the outcome, we have financial consequence. And measurement of it is putting probabilities on these consequences. Failure mode is a set of specific conditions or variable settings that results in a failure, meaning that what was a risk now becomes reality. We are facing a problem that we anticipated but haven't really thought about, between bridging this and that functionality, one variable. We were hoping to get Joe to work on it, but Joe is not available. we were trying to hire someone else or a subcontractor and he couldn't come. So you've got a number of variable settings, which together means a failure. We call this a failure mode. And assessing the probabilities is reducing uncertainty, which allows us to make better decisions as we go. Measurement is a quantitatively expressed reduction of uncertainty based on one or more observation. It's quantitative. It is based on evidence. And assuming that we can measure this evidence, that we can get actual data, we have a measurement system. Clarification chain. If it's a matter, it is detectable and observable. If it is detectable, it can be detected as an amount or a quantity of a range of amount. And if it can be detected as such, then it can be measured. The scale may be ordinal. It may be judgmental with criteria and judgment involved. It can be strictly observational. It can be counted, but there is a scale. It can be repeatable, meaning that the same person seeing the same phenomenon will come up with the same amount. Reproducible, two different persons seeing the same phenomenon will come up with the same amount, the same measurement. Those are very important qualities we would like our measurement systems to have. Systemic error is an inherent tendency of a measurement process to favor a particular outcome. A bias then. We have a tendency to overshoot. We have a tendency to overestimate. So accuracy is low systemic error. On average, we're right. But then there's random error as well. An error that's not predictable for individual observation, not consistent or dependent on known variable. So random error occur randomly. We have no way to attribute it to a specific variable. We'll define precision as low random error. Visually, it looks like this. The target we're trying to reach here is the center, of course, and we have mistakes, we have variations, we have deviations from that target value. This is imprecise, meaning that there's a lot of random error. This is very precise in that there are very low random error, but in both cases you have a bias. You're systematically to the left and below. That's inaccurate. Accuracy, on the other hand, is that on average you are on it. But in this case you are on it and precise. In this case you are on it but imprecise. There is a lot of random error. But when you're accurate, there is no systematic error. Of course, you're shooting for that type of situation. And in an important measurement system, you want to characterize your measurement system in that way, trying to have it as precise and accurate as possible. Let me use a different metaphor to discuss this. Parking space. You're trying to park in between two lines. Let's call this the voice of the customer, the target, the specification. And let's take the width of the car as the voice of the process, the total variation that the process produces. You're trying to get the voice of the process within the voice of the customer. The bigger the voice of the customer, the wider, of course, the easier it is. But also, the wider the car, the more difficult it is. Small car will be easy to park. This here is, of course, way off the side, and if it's a wide car, that would be more probable that it will occur. If you've got a small car, you don't really worry too much about it. You've got plenty of space either way. The metaphor here is that a process that is very precise will have low random variation, will in this sense be a small car. You will not need an army of person to verify, to check accuracy, to be very focused. It is so precise that it will be within. Accuracy will be less important in this sense for this type of car as well. In a dynamic way now, you're not trying to park, you're trying to drive a car. You're getting feedback information and your process is moving around according to a number of variables, some of which you control, some of which you don't, which is the alignment of the wheel, the wind, the direction and intensity of the wind will impact you. This is more like process control in real life. It is actually process control. An airline, for example, has the same is a pretty good metaphor as well, with the width of the runway as the voice of the customer, and the width of the aircraft as the voice of the process. If you look at it in a dynamic fashion now, you've got the voice of the customer, and the process is trying to get right in there, with consequences the closer you get, and if you get outside, of course, the consequences here would be dire, and you see some variation of the center, of course. And it is dynamic, you're moving on each side, you're controlling some variables, and you're adjusting for variables that you don't control. You can adjust the wind, but you can adjust your angle, your variables, your sail, according to the wind. Let's formalize these metaphors in terms of concepts and metrics now. Voice of customer is defined. Here's the gap between a lower specification limit and upper specification limit. Sometimes you only have an upper spec. Sometimes you only have a lower spec to meet. This is the voice of the customer. This is the voice of the process. The capability ratio, then, is the ratio of the voice of the customer to the voice of the process, represented by the plus and minus 3 standard deviation each way, with the goal of reducing that to reducing the variation of the process, but increasing the ratio of capability as you do to 1 and eventually up to 2, which is the standard goal in a Six Sigma organization. Now, if you're symmetrical like this, you see that the capability ratio is less than 1 here, and you have improved it to 1.2 here. How do you do that? By isolating variables, critical variables that impact the mean, and critical variables that impact variation, and some variables that impact both. You do that in the analyze phase. You isolate variable, you separate them, you characterize the process. When you move to the improve phase, you find ways to better manage these variables to optimize their value in such a way that your process becomes capable and you can become slightly inaccurate, shift and drift, as I will explain in a second, while still delivering quality, meeting customer specifications. This guy, now here the difference is that you are not centered. Both distributions are off-center. So the ratio of capability cannot be the same here. The calculation of this to that is a poor reflection of your capability to meet customer requirement. When you're off-center like this, what we take is the difference between the mean, the central value, and the closest customer specification, and divided by half the voice of the process. That gives us a fair estimate of the capability ratio, with the goal of improving that by either improving accuracy or improving precision, or both, in such a way that your process becomes capable. This guy is also not capable, but he's quite precise. What we have to do here, the task is really to increase accuracy. So by finding the right variables, in this case we are slowly moving the process toward the CPK, the K indicating that we are off-center, by doing both things, improving precision, improving accuracy. In this case we are merely maintaining precision while improving accuracy, bringing the process into a capable situation by identifying the variables that impact this, by putting a team together, by doing detailed analysis, and by generating ideas for solution. And of course, you can measure your progress as you go, measuring what we call CP and CPK, and reaching a better level, and trying through continuous improvement to bring it up to a level where you don't have to worry about it. Robust quality. Let's look now, if you recall, I started with parking a car. Then I went on to driving a car, even driving a plane. So this is, the parking part is static. The driving is much more akin to the real life situation of managing an ongoing process. So let's transfer this, which is static, which is the sum of a number of variations that have occurred over time, but we lose the time dimension here. We lose a lot of information. So this distribution, plus or minus a 3 sigma both ways, can be on a time dimension, can give you a very interesting diagram with the mean, the upper control limit, and the lower control limits. And if you measure variation over time, this gives you information. While variation is the enemy of value, it is the friend of anyone who wants to characterize and thus improve the process. When there's a variation, there's a reason. Sometimes the reason is a sum of random actions of which you can't get much information out of. Sometimes the variation is such that a special cause is at work. Something is happening. The process is speaking to you. The voice of the process, if you listen to it, is telling you something. This is a simple example drawn from Richard Landon. It's the time he takes to drive to work. Those are 3 sigma both ways, and you've got, of course, some points which are out of the 3 sigma range. Now, if you recall that within plus or minus 3 sigma, you've got 99.7%. Whenever you get a point like this, you know that, hey, something's changed here. Unless, and there is a possibility, 0.3 of 1%, and the further you are, the smaller that possibility. The greater probability is that you're not in that same situation anymore. Some key variable or special cause has happened. In this case, of course, he had a flat tire. That would take longer. There he had a football game to go to, so he drove faster. In this case, he got into a traffic jam, meaning that there are special causes that intervened in that specific instance that explains the variation. This number, if you're away from it and you just see the number, should tell you that something happened, and if you want to understand, characterize the process, you should investigate. In this case, maybe he was going to a football game, but then he got caught, and in this case he flew in. So there you have it. This is variation from one iteration to the next, and to interpret it, you need to think statistically. Within this range, variation is within normal parameter. If you recall the normal distribution here, you are within the normal parameter. The voice of the process is not telling you anything. When it's out here, it's telling you something. Other patterns, for example, if it's increasing all the time, if you got a pattern like this, you may be within the limits, but something is obviously not random here. There is special cause. You could be cyclic like this, and again, this is not random. Any non-random pattern means that there is special cause. And to determine whether it's random or not, you need to think statistically. Other typical process problems include what we call process drift. Process slowly drifts backward. This process here slowly drifts upward. That's classical, and we shouldn't rely on our intuition that there seems to be a line. We should not only think statistically, but we should bring statistics to bear to make sure that our intuition is well supported by probability theory and odds calculation based on facts. Statistics is a science of the unknown. it does bring some order and science to things that appears to be random, and avoids corrects our systematic biases and intuition, which tend to be quite inaccurate. We are not very good, typically, in terms of assessing probability. We misjudge. So this is where statistics come in. The voice of the process and understanding it are key to improvement. Statistic is the language of processes. The process drift is typical. Process shift is more like the process is quite stable here, then it jumps all of a sudden. A process shift is characterized by a one-time element that occurs at a specific point in time and that is reflected in the data by a jump. Shift and drift are very different problems, and the underlying facts are quite different as well. So being able to detect it leads us in our investigation to look for specific element. If there's a shift, I will look at that point in time what happened. If there's a drift, I'm looking for a variable or a combination of variable that is slowly changing value as a result of some sort of time-based phenomenon. Process improvement, starting from a situation where the process is totally out of control, unpredictable. This is being the target here. This process still has a very imprecise, but it is accurate and it is predictable. So it's been brought under control. And in this third version here, the process has reduced variation. It is more precise and more likely to be within customer requirements and to require less verification and control. Produces fewer defects and requires less control as well. And at that point you can also try and make the target more difficult and reach for maybe market segment with more tougher requirements. This is an example from the NHS in the UK, the National Health Service Innovation Group. They show the time required waiting time for chemotherapy. Starting in 2002, you've got the process as it was at that time. And then they started doing some improvements, reducing variation and increasing precision considerably, as well as increasing median time. So they are meeting increasingly demanding customer requirements, and they are meeting them more reliably. What this type of system, information system, gives you is an ability to listen to your process and to detect when something is happening, to find out that information and not lose it. The learning organization is an organization which systematically, when something is happening, maybe something costly is happening, captures the information and avoids the defect in the future, incorporates the solution in the future versions of the process. And you can measure your progress as you go by measuring your process capability immediately. Let's look at the takeaway from this short presentation. Process mapping is best performed by layer, trying to maintain an even granularity at each layer. The mapping should be validated. So, meaning this is the first part of the video. Start with eye level mapping, take it down to street view level, maintaining about the same level of detail as you go down. Process mapping allows for variable identification. If you can't measure it, you can improve it. Valid measurement system must be developed for potentially important variables. The system should be practical and display sufficient level of precision and accuracy. It should be repeatable and reproducible. By practical, I mean that you'd like it to be as simple as possible, as cheap, fast, and accurate as possible. Once we can trust the data, and once we have clearly established the voice of the customer, we can calculate process capability and set a target value, and measure progress as we go, progress towards the goal. Statistical thinking is the key to understanding variation. Not wasting time with random variations which are perfectly within normal range, but not letting go learning opportunities stemming from abnormal variations. Understanding variation is the key to understanding the process and thus to improve it. Drawing conclusions from data without previously validating the measurement system does not lead to knowledge. It leads to superstition and dooms to failure any drives to becoming a learning organization. Once you come out of the measurement phase, you have described your process, you have identified your variables, you've developed valid measurement system that measures the right thing accurately, precisely, and your measurement system is both repeatable and reproducible, meaning you have data to analyze safely without risking going into superstition. This output is an input into the analyze phase, which is the object of the next video, which will produce a diagnosis. Critical element before you move to the improve phase that comes after. Thank you.